Hi, my name is Lori, and I'm a support engineer with GeoSlope. I've created a series of getting started tutorials for new users to GeoStudio. So if you're brand new to using the GeoStudio software and you're not quite sure where to start, then you've come to the right place. These tutorial videos have been designed to help walk you through the basic steps of creating a simple model using GeoStudio. Topics that'll be covered in this series will be how to use define to set up a numerical model, using the solve module to compute the numerical solution, and how to use contour to view the results and to gain a deeper understanding of the problem you're modeling. You can pause, stop, fast forward, or rewind these videos at any time by using the controller bar positioned at the bottom of the window. If English is not your first language, you might find it helpful to print out a copy of my script, which is available as a PDF from our website. So let's get started. Here are some results obtained using Seep-W to analyze unconfined flow through an earth dam. The results include total head contours, velocity vectors, and the location of the water table or zero pressure contour. For this analysis, we start by creating a new Seep-W project from the start page of GeoStudio. Select what type of analysis you're going to do and give it a name and description. The first time you start working with Seep-W, it's helpful to learn what different toolbars exist. Many of the drop-down commands are also available as individual icons on the many different toolbars. You can familiarize yourself with the toolbars by toggling them on and off. When developing a numerical model, the first step is usually to set the working area. This defines the size of the space available. The working area may be smaller, equal to, or greater than the printer page. Step is to set the scale. The scale should be set such that the minimum and maximum extents in Seep-W match those required for the analysis. Define the X and Y minimum and maximum extents to find an approximate scale, and then fine-tune it to use a 1:1 aspect ratio. A background grid of points will help you draw the problem. It's often helpful to sketch an axis. The axis is drawn by moving the cursor from the bottom left corner and stretching it outward. The number of increments can be adjusted using the Set Axis drop-down menu. Before defining the geometry in Seep-W, it's convenient to first sketch the problem. Select polylines from the Sketch menu or use the Sketch polyline icon. Use the cursor like a pencil, clicking the left mouse button to create a series of lines to outline the problem features. The lines are objects which can be adjusted or deleted using the Modify Objects command. The approach to use when developing a numerical model is to draw the geometry, create and assign materials, create and assign boundary conditions, and then finally to review and fine-tune the finite element mesh. Let's start by drawing the geometry. Individual soil regions are created using the Draw Regions command. Click the left mouse button to create region points. Once the polygon region has been closed, you can either continue to draw additional regions, or you can right-click the mouse button to exit the Draw Regions mode. Materials are first created and then assigned to geometry objects. Choose Materials from the Draw drop-down menu. Click on Key In to create a material. Add the material, name it, and select the material model from the drop-down list. For a steady-state analysis, only a conductivity function needs to be defined. The ... button is used extensively in GeoStudio to indicate that additional features can be accessed. Click on this button to create a hydraulic conductivity function. Click on the Add button, give the function a name, and select the type from the drop-down list. defining a data point function of matrix suction, which is a positive value, and a hydraulic conductivity. Often a 2-point function is sufficient as a starting point. Additional points can be added and adjusted by editing the function directly. Once you're happy with your function, you can then close the Key and Hydraulic Conductivity dialog box to be returned to the Key and Material Properties view. The function has now been assigned to the soil. The material can now be assigned to the geometry regions. It's a good idea to save your file frequently. Boundary conditions are created and signed in the same way materials are. Sometimes it can be helpful to sketch additional information on your geometry so you know where to define your boundary conditions. The reservoir level for this analysis is going to be at an elevation of 11 meters. Select Boundary Conditions from the Draw menu. There are already 2 commonly used boundary conditions available for you to modify or use. You can also create your own boundary condition by clicking on the Add button. For this example, we need a boundary condition that will reflect the full reservoir level of 11 meters. Once the boundary conditions have been created, you can then apply them to the region geometry. A zero pressure boundary condition will be applied to the downstream toe, which is a geometry point. A potential seepage face boundary condition will be applied to the downstream face, which is a line. The potential seepage face is a special boundary condition that is used when you want the solver to locate the position of where a potential seepage face might develop. To break up a region edge so that you are only applying the boundary condition, such as the reservoir total head, to a portion of the edge, you may need to insert a region point. Boundary conditions can be easily removed from the geometry as well. Now that the geometry has been drawn, the material properties created and assigned, and the boundary conditions applied, it's time to review the finite element mesh. You can view the finite element mesh using Draw Mesh Properties. The meshing algorithm in Seep-W is defaulted to use a global element size. To make the mesh more finely discretized, type in a smaller global element size and the mesh will be updated automatically. You can apply meshing constraints to individual geometry objects. It's often best to start with the default mesh and then constrain the mesh only if necessary. The finite element mesh will disappear once you leave the Draw Mesh Properties view. If you want to leave it on, you can click the View Mesh icon on the View Preferences toolbar. One of the objectives of this analysis was to compute the amount of flow through the earth dam. To do this, we can use a flux section. Flux sections are used to identify elements where you want the software to compute and report the amount of flow crossing these elements during the solve process. Now it's time to solve the problem. The solver for Seep-W can be launched by clicking on the Solve icon. Click the Start button to activate the solver. You can view the results directly by clicking on the contour icon in the Analysis toolbar. By default, the contour results will include velocity vectors, the location of the zero pressure contour, and total head contours. The flux section results can be viewed by selecting flux labels from the Draw menu. Clicking on the flux section will make the total flux value appear. This value is the total amount of flow past the flux section per unit depth. Flow paths represent the path that a drop of water would travel from the reservoir through the dam. Draw a flow path by using the appropriate pull-down menu and then click the cursor anywhere within the profile. You can remove a flow path by clicking on it a second time. It's important to remember that flow paths are not the same as flow lines. Remember, at any time you can change the way the contour information is presented by using the View Preferences pull-down menu. You can also retrieve information from specific locations on the profile. Select View Result Information and then click on the location that you're interested in. If you hold the Control key down, you can gather information from several different locations. You can label your contours using Draw Contour Labels. There are many different types of parameters that you can contour. Use Draw Contours to view some different results. 3 default contour options are available, but you can also add other options to the list using the Add button. It's often helpful to look at a graph of results. To create a graph, choose Graph from the Draw menu. There are many different graphs that can be developed, including the pore water pressure profile through the middle of the dam, or the boundary fluxes that are leaving the mesh from the nodes on the downstream seepage face. New to GeoStudio 2007 is a reporting feature. If you need to generate a report of your input data, select Report from the View menu. Once you save the report file, your default word processing program will open with a generated report. You can now insert pictures, apply style templates, or add and delete data. If at any time you need help with understanding a dialog box, you can click on the question mark in the top left corner to access the online help, or use F1 on your keyboard. You can also switch to the Analysis Start page, which has PDF copies of all the engineering books for GeoStudio under the Documentation section. These books are very helpful in describing the features in the software and the theory behind them. You can also search through the examples database using specific keywords. And when you're done, you can return to your analysis by clicking on the analysis list. One of the powerful features that's new to GeoStudio 2007 is the ability to run many different analyses within the same project file. The geometry is considered project-specific, but you can change boundary conditions, material properties, or even different types of analyses. One example might be to now use the Seep-W computed pore water pressures in a stability analysis using Slope-W. Or you could use the results from the steady-state simulation as a starting point for the transient simulation, where you might model rapid drawdown of the reservoir. You can also include multiple analyses in a project file that do not depend on each other. It's a convenient way to explore different scenarios for the same geometry. As an example, let's rerun this steady-state simulation, assuming that a blanket drain was installed at the toe. Since the materials assigned to the regions are going to remain the same, I'm going to create a clone analysis instead of starting a new one. The results are independent of the first simulation we did, so the two simulations are considered to be siblings of one another. By reapplying boundary conditions to reflect the toe drain, I can resolve the problem and view the new results for the blanket drain installed at the toe. We've reached the end of this introductory lesson. Not all of the powerful features of Seep-W have been used or discussed during the lesson. Specific details about each command are given in the online help and in the supporting documentation for Seep-W. Thanks for watching.